said number 2 or number 22?
Number 2. So do you see number 2?
Yeah.
So it says a service station charges a battery using a current of 6.7 amps for 5 hours. How much charge passes through the battery? So we've identified that they're asking us to solve for charge, which is Q, right?
Mm-hmm.
And now we just have to think.
Did they give us the current? It's 4.6 amps.
You're looking at number 4.
Number.
You're looking at number 4.
They gave us
6.7, exactly. So when we're looking at that middle equation that I circled for you, we would be prepared to put in 6.7 here, right? And then what would we do for delta T? What would we stick in delta T?
Stick on the side. What is H? H is hours.
Yeah, H is hours.
H is hours? I thought it was going to be HR for hours.
Yeah, that actually is more common to see HR for hours, but if you see H, it also means hours.
5 hours.
So can we stick the number 5 in there?
Yeah.
The metric system unit for time is?
Minutes.
No.
It's in hours, but like we convert it to seconds.
Seconds, yep, exactly. Everything that goes into an equation in physics has to be in meters and seconds and whatever the metric system units are. So they can give it to you in hours, but you'll have to convert that over to seconds.
All right.
So you want to try to work on that one since that's your first homework problem?
Yep. Yep. Seconds, 1 hour times 4. So there's 18,000 seconds in 5 hours.
Yep. So what are we getting for an answer? Jeremiah?
One sec. We get 120,600.
Yep. What will the unit be?
Charges.
What is it?
Electrons.
So remember, we're solving for Q, which is charge. So what will the unit for charge be?
Coulombs.
Coulombs. Yep, you got it. Good job. And if we wanted to express that in scientific notation, what would we put?
1.2.
Yep.
Times 10 to the 5th.
Yep. Good. So that's number 2. If they kept it plugged in, if this is a service station that's charging a battery and they kept it plugged in for 10 hours instead of 5 hours, how would the answer change?
It'll
By what factor?
By factor of 10 hours. 5 hours.
So the original charge that we worked out was a 5-hour charge, and you got your answer on the page. Now we're rethinking the problem and thinking, what if we charge it for 10 hours instead of 5 hours?
It would increase by a factor of 5 hours.
So think of it this way. Coming back to this equation that's in the box here, notice that Q, the total charge that goes into the battery, is proportional to delta T, right?
Yeah.
So if we go from a 5-hour charge to a 10-hour charge, by what factor are we increasing the charge time?
2.
2 hours. Yep, 2. I didn't mean 2 hours. By a factor of 2. It's twice as long, 10 hours compared to 5 hours. So that means by what factor will the charge be? If delta T goes up by a factor of 2, then Q will go up by what factor?
Factor of 2.
Exactly. And what would your new answer be?
It would be 241,200.
Yep, exactly. It would double, right? So if you charge for anything for twice as long, you'll put twice as much charge into that thing that you're charging. So your new answer would be 2.4 times 10 to the 5th, right?
Yeah.
What if you charge for only half as long?
Cut down by a factor of half.
Yep, and our new answer would be 0.6 times 10 to the 5th, right?
Yeah.
Yeah, so you see that idea, right?
Uh-huh.
Okay, one more. Again, because I find these questions the most important, because this is really where it separates students who are just focused on equations and getting the right answer, and then students who can also focus on equations and get the right answer, but also have critical thinking skills. So I'm going to give you one more.
All right.
Let's say we, again, do the same thing that they said. It's a 6.7 amp current flowing into the battery at the service station for a total of 5 hours. They asked how much charge goes into the battery, and we had our answer, 1.2 times 10 to the 5th, right?
Yeah. Yeah.
And now someone says, we'd like to double the current, because actually there are devices that charge batteries. You might know that. And I don't mean like phone batteries. What I'm referring to is there are like car charging, cars obviously have batteries, you know that, car batteries. And when your battery is low, you can connect that big car battery to a charger. And there's buttons on it. You may not have seen one before, but I'm telling you, they exist. And when you have a dead battery, you bring it to, disconnect it, you bring it into your garage, and you'd plug in this unit that you'd have to buy that charges big batteries. And there's big buttons on it. It'll say, would you like to do the 2 amp charge, 4 amp charge, 8 amp charge, right? And that means if you press the 2 amp charge, it means it's going to send current into your battery at a rate of 2 amps. You press the 4 amp button, it's going to send electricity into your battery at a rate of 4 amps or 8 amps or whatever button you choose, right?
Yeah.
Okay. So for this question, the question is, what if we decide to double the current, but we're still going to charge it for 5 hours? That's not going to change. We originally did it for 5 hours at 6.7 amps. Now we're going to charge it also for 5 hours, but at twice the current at 13.4 amps. What would your new answer be? You double the current, but not the charge time.
Double.
Good job. Yep, exactly. Nice. Good job. Because notice, again, back in this equation, right? Notice delta Q is also proportional to the current.
Yeah.
Right? So if you keep delta T the same, which is, it's always going to be a 5-hour charge, but you double the current from the 2 amp button, and now instead on the next, deliver twice as much charge to that battery in the same amount of time of 5 hours.
All right.
Right? Also, let me point out something practical. In cars, you have like the auxiliary ports, like where there used to be they used to be called cigarette lighters, but I don't think they make them like that anymore. You know what I'm talking about inside of a car?
Yeah.
They used to have, back in the day, those were actually cigarette lighters that you'd push in and it would get hot, and you'd pull it out and it would be for lighting cigarettes. But nowadays, I don't think for fire hazards, they don't put them in there, but you still have that as a charging spot, right?
Yeah.
And then what people nowadays do is they plug in, if you watch my drawing, they plug in the device that looks like this, and then there's 2 USB ports.
Mm-hmm.
Have you seen this? And then right here, this will say 2.1A, and then this one will say 1.0A. What does that mean?
The amount of amps that pass through both each one of them.
Right.
USB ports.
Right. So if you want to charge your phone, to be honest, I don't know why they designed a 2.1 amp port. Why not just a 2 amp port and a 1 amp port? I don't know why it's 2.1. But let's just say it was exactly a 2 amp port, just to make it easier. If this was in fact a 2 amp port, and then you have also the choice of plugging your phone to charge it in, you can choose to go to the 1 amp port. Which one will charge faster?
The 2 amp port.
By what factor?
By factor 1.
So let's come down to
1.1.
Let's come down to this third equation. You see the third equation I've circled for you?
Yeah.
And I'm going to erase your problem. I mean, you got it right. That was good. But this part's important. So if we stare at the third equation, way down on the bottom over here, delta T equals delta Q over I. How does the charge time, delta T, relate to the current? Directly proportional or inversely proportional? Looking at that third bottom equation on the bottom left.
Inversely proportional.
Inversely proportional. This is an important idea. It means if you decide to plug into the 2 amp port, you're increasing the current by a factor of 2 because you're not plugging into the 1 amp port, you're plugging into the 2 amp port, right?
Yeah.
So your current's going up by a factor of 2. What will the charge time, delta T, do?
The charge time will
If I goes up,
increase.
yeah, if I goes up times 2, delta T will go up or down?
Go up.
You told me they're inversely proportional.
Yeah.
So if I goes up, what will delta T do?
It'll go up as well.
No, that's directly proportional.
It will go down.
It'll go down times what?
As a factor.
If I goes up by a factor of 2, delta T will go down by a factor of 2. So that means if you plug into the 1 amp port, it might take an hour to charge your phone. If you plug into the 2 amp port, it might take blank to charge your phone. What would blank be? It takes an hour to charge your phone in the 1 amp port. How long would it take you to charge in the 2 amp port?
30 minutes.
Exactly. Going down by just an amount of time that's 2 times less than an hour, which is 30 minutes, right?
Mm-hmm.
So that's what it means to take 60 minutes is an hour, divide by 2. When you say go down by a factor of 2, means you take the number and divide by 2. 60 divided by 2 is 30 minutes, right?
Yeah.
So does that make sense also to you?
Yes, it does.
Okay, because that is practical. That's a really powerful and practical idea that is so relevant to what we're doing with all of our electronics, and 99.9% of people don't understand any of this. So it's useful for you to understand some of it.
Got it.
Yeah. All right, so let's move on to your next one. Let's just take a peek at number 4. All right, so I think we got to switch gears at this point. There's something completely different that you need to learn. It's called Ohm's law.
Right.
Okay, so it's not completely different. It's related to electricity, but it's quite a shift from what we're talking about right now.
We got it.
And that's what your number 4 is. Number 4 is an Ohm's law. So I'm gonna, if I can, let me see here. I'm gonna try my best. Last time I did this with you, I ran into issues. I'm gonna cross my fingers and hope that it'll be okay today. I'm going to go to an app. I would like you to see a visual, something visual, okay?
Mm-hmm.
So let's see if we can do that. I use this particular website all the time as a teacher for my students. Sometimes I just project it on the board and let them watch what I'm showing them. Other times, they actually all have Chromebooks at our high school, so they go on their own Chromebooks and bring up this website and do certain activities. But this one's one of my favorite out of all the ones they offer because it gives you a full circuit that you can build. So let me just pull it up. Hope that it works. So now what we're doing is changing from just talking about current and charge time, which is what we talked about for the first hour, and now we're talking about circuits.
All right.
Okay. So can you see the blue screen?
Yeah.
Okay. So what we have is, these are wires. I can bring a battery in, and then maybe what we'll do is, actually, now that I think about this, I haven't taught you about resistance yet. All right, I'm going to come back to this. We'll come back to that in like 10 minutes. I now have to teach you about resistance, what's called electrical resistance. I haven't even learned voltage yet. You haven't learned about voltage yet either, right?
No.
No. Okay, I'm backtracking then. Sorry. So you learned current. Check.
Yeah.
So there's this thing that you are going to need to know, hopefully by the time we're done, called Ohm's law. And Ohm's law involves voltage, current, and resistance. We've done current. Now I got to do voltage and resistance so you understand what those are.
Okay.
All right. And once that's the case, then I can go back to that visual thing and let you see how it all comes together. All right, so now we're going to do what's called electrical resistance. When electricity or electrons flow in a wire, there is a certain amount of resistance . Okay, so on a very small scale, you can imagine a bunch of atoms. This is a very simplified idea, but it gets an important idea across. So all these circles I've drawn are just think of them as atoms. Okay?
Yeah.
Let's say they're all copper atoms, and they're all inside this cable, because all of our cables that are all around us, if you peel off that rubber, inside is copper, and it's all wound together. And electricity now flows through the copper. When electricity flows, an electron coming in has to physically bounce. It literally jumps. It jumps onto an atom like this, and then just for a brief moment, and then it jumps over to the next atom, and then it jumps over to the next atom, and it just keeps on bouncing, ultimately to the other end of the wire. So they jump over to the atom, they stay just for a fraction of a second, and then something pushes them over to the next atom, and then something pushes them again, and then ultimately they'll kick out the back end of the wire. Okay?
Yeah.
Now there's a certain amount of resistance that they feel as they try to make this passage from one atom to the next to the next. All things in nature that involve motion, there's always some sort of resistance that we have to fight through. In our big macroscopic world as people, we deal with friction, right? That's a resistance that impedes our motion, it slows us down, and we always have to put extra energy into to overcome it, right?
Yeah.
How about water flowing inside of a hose? As it's flowing, is there some friction in there? Does the water rub against the hose itself on the outside of that inner wall of the hose?
Yeah.
Yeah, and that's why if you had a flat hose sitting on the street with some water in it, and you put your mouth up to one end and blow it, the water would start moving, but then if you stopped blowing, would the water just keep on going along the hose forever?
Yeah.
It would? If you stop blowing, you hold it up to your mouth, one quick blow, and then you watch the water, oh, it starts to move because you put a force on it. Water starts moving, but does the water just keep flowing? If that hose is 10 miles long, will the water keep flowing forever and actually make its way 10 miles just from one little blow?
No.
No. It'll only go a few feet and stop, right?
Yeah.
What stops the water from continuing to go forever?
The friction.
Exactly, the friction, the resistance to that, right? And you have to keep blowing, keep putting energy in and a force in to continue to make it move. It's the same thing when we're talking about electricity. When electrons try to make their way through a cable, there's a certain amount of resistance that they feel from the atoms themselves that are often slowing those electrons down and decreasing the current. And you have to keep putting in force to keep pushing them so they keep bouncing one to the next and keep on going, okay?
Yeah.
So that's called electrical resistance. And the amount of electrical resistance you have depends on what material you choose to make your cables out of. So it turns out that copper actually has a relatively low resistance, but it's not zero resistance. That copper does definitely resist the flow of electricity around us in our homes and in all of our electronics. Had we used gold, if we made gold threads and made all of our wire out of gold, gold has an extremely, extremely low resistance and current would flow more easily, but gold is extremely expensive. No one's going to make a home wired with gold, right? Silver, same thing. Nice properties for electricity because it has a very low resistance. Again, very expensive. So my point that I want you to recognize is that the choice of your material that you're going to make your cable out of affects the resistance. And no matter what you choose, there's always some amount of electrical resistance in the wires, in the material you've chosen. It varies depending on what material you choose, but there's no material that on a planet, and we don't believe there's any material anywhere in the universe that you could find that would be zero resistance, zero electrical resistance to the flow of electricity. That doesn't exist. Okay, so materials technically break into two categories. They are either called conductors or insulators. Did we talk about this on during another lesson? Maybe. Conductors and insulators, have we ever talked about that?
Probably so, when we're talking about thermos.
Well, what's that? I'm sorry, one more time.
I feel like we spoke about that in Coulomb's law.
Okay, so conductors are all metals. Conductors allow electricity to flow easily. They allow the electricity to flow easily through. They're all called conductors. So all metals are considered conductors. Insulators, on the other hand, it's hard for electricity to flow through. And so examples of insulators are anything that's not metal. So wood, plastic, PVC, styrofoam, rubber. These are all considered insulators. The one we've chosen as our primary insulator in all of our electricity is which one out of that list?
Rubber.
Rubber. Every single wire is covered in rubber, right?
Yeah.
And the reason is we know there's electricity flowing on the metal inside of that. Because if you take any of the cables and grab a knife and slice it open, you peel away the rubber and you'll find metal threads inside. The electricity flows along the metal threads because metal conducts, right?
Yeah.
The rubber is on the outside so that when you grab that wire, you don't get electrocuted, right? Because it doesn't flow through the rubber. Rubber's an insulator. So conductors, generally, all conductors have low resistance, and all insulators have high resistance. And you would technically add the word electrical here. So conductors have low electrical resistance, and insulators have very high electrical resistance. Okay?
Got it.
Now, resistance has a unit named ohms. The name of the unit for the SI unit is OHM, which normally has the symbol.
Yeah.
That's actually the symbol for ohms.
All right.
So you could have a cable that has 2 ohms of resistance, or you could have a cable that has 10 ohms of resistance, or you could have a cable that has 100 ohms of resistance. And that means that all of those cables have different resistances to electricity flowing through them. The 2 ohm resistor is the least resistant, so electricity would flow through pretty easily through that one. You decide to pick a 100 ohm cable, you can still make electricity flow through it, but it will be more challenging, and you would have to push harder on the electrons to fight through 100 ohms of resistance versus only 2 ohms.
Got it.
Does that make sense? Okay. So let me try to think. Okay, now I know where I'm going to go next. No questions about resistance? Let's do our next little picture here. Think of a hose. This is how I've taught this for a long time, so I use it this way. I use the same illustration because I think it works well. So imagine what we're doing is I'm going to do an analogy for electricity flowing through a wire and relate that to water flowing through a hose. Okay?
Okay.
So this is a hose, which is like a cable.
Mm-hmm.
And then we have water flowing which is like current. Like electrical current. Okay? And then we have to make the water move in a hose, you have to put some input force to move. Because if you take away that force, the water won't move. It'll just sit inside of the hose, right? Jeremiah?
Yeah.
So if you don't apply a force to that left side of the hose, then the water will just sit there inside of the hose. How much current would that be? If the water's not moving, it would be zero, exactly. 0 amps, 0 current. You, on the other hand, pick up that part of the hose and blow with a certain force, water starts moving, right?
Yeah.
So the water moves in response to the force that you're applying on that end of the hose. That makes sense, right?
Yeah.
So this input force is called voltage.
Okay.
Voltage is, voltage is a result of electrons piled up in a confined space.
Okay.
So let's just say you have a piece of metal, a metal sheet.
Mm-hmm.
If you put 1 electron on there, that's not very much voltage. But when you put 2 electrons on there, do those electrons want to repel each other? Or do they like being together? Are they happy together, or do they want to get far apart?
They want to get far apart.
They want to get far apart. They repel. If you put 3 electrons on there, they're still repelling, but more repelling, right? Because now you've got 3 electrons trying to get away from each other.
Yeah.
More pushing force. This is the Coulomb law we talked about before, right? How about 4 electrons or 5 electrons? You keep jamming them in there. jamming them in there. Eventually, you're going to have so many electrons jammed onto this plate that becomes what's called a high voltage.
Got it. Yeah.
Is when many electrons, well, I won't say it again, it's this idea. When electrons are piled up in a confined space, right? So now the point is they are pushing apart, but they can't just jump off. They can't just jump off and fly through the air. They're kind of stuck on the plate. And each time you keep jamming more electrons on there, they're more bound up and there's more energy that's repelling, they want to just fly off, but they can't because they're stuck on the plate. If you come over to that plate and connect a cable, like I'm drawing here, well, a conducting cable, what will those electrons do? What will they do if you touch a metal cable to that plate? Is that a way off the plate for them?
Yeah.
Yeah, because they can flow through the metal wire that you're bringing over, right? So as soon as you touch it, those electrons immediately will empty off that plate and they'll flow out because they're pushing apart. They want to get off the plate, but originally there's just nowhere to go. It's like being stuck in a room. And then somebody opens the door, everybody can go out. That's what connecting that wire is doing. It allows them to come off of the plate, and that's actually what produces current.
Could I hold on with this on me real quick?
Sure.
Are you still there?
Yeah, I'm still here.
Okay, perfect.
So voltage is created by putting electrons into a certain space and confining them. That's what batteries are. When you have a battery, you're charging your battery, you're forcing electrons into that battery onto some area of the battery. It might be a metal plate inside there. And you just keep on jamming them in, forcing them in. And when the battery becomes fully charged, there's lots and lots of electrons all stuck on a plate. But they're stuck there. They can't get out. It's like I had said, all these electrons are just stuck on this plate and you're holding it in the air. They can't leave the plate. So when you connect a wire, though, to the plate, they all flow off. And that's like putting a battery into a remote control. As soon as you put the battery in what do you connect the battery to? Behind the remote control, when you open it up, you see the little circles of metal, right?
Yeah.
So they flow right into that metal and then through your remote because it's a way out off this plate for them and through your circuit.
Got it. Yeah.
Okay? And so voltage, I'm going to now take the word force away over here and just put the word voltage here. So the voltage is what pushes electrons through cable. Because can you look at the bottom right of what my drawing is showing?
Yeah, I see it.
So the bottom right, see how there are now 3 electrons in that wire that I showed connected to the plate?
Yeah.
Who's going to keep pushing them through?
The current?
Yeah, but are there still electrons on the plate?
Yeah.
Yeah, and the electrons that are still on that plate, they're pushing on each other, and that pushing gets transmitted into the wire and allows the ones that are in the wire to keep on moving. So that pushing force keeps coming from the battery, and it transmits through the wire and allows the electrons that have made their way into the wire to just keep on going.
All right.
So that's called voltage. Resistance, if we come back to my hose, would be like rocks. Well, before we talk about the resistance part, voltage is, V stands for voltage. Voltage is proportional to current, which means if you push harder on the electrons, right? Doesn't that make sense?
Yeah.
Like if you blew harder on the hose, like a blow, really hard blow, you'd expect the water to flow more rapidly in the hose. And if you diminish your pushing force by blowing less hard, the current will still flow, but not as quickly. Does that make sense?
Yeah, it does.
So those are proportional to each other. Voltage and current are proportional. And the other part is, how does resistance, the wire, play into this? Well, in my illustration and analogy that I often use is, now imagine jamming rocks. These are rocks that I'm jamming into my hose. If you jam rocks into the hose, that's like resistance, right? It's resisting the flow of water. The rocks, so the water flowing was like the current. The blowing with your mouth on the end of the hose is like the voltage. And now rocks being jammed into your hose are like resistance now, because they resist the flow of water through the hose, right?
Right.
And so if you have a very high resistance wire, that means this is really jammed with rocks. What will that do to the current? Lots of resistance. Will that make a lot of current, or will that make just a little bit of current?
A little bit of current.
Exactly. So how will current and resistance be related to each other? Would those be directly proportional or inversely proportional?
Directly proportional.
So if we said current is directly proportional to resistance, and R is now the symbol for resistance.
Well, it makes them inversely proportional.
Yeah, that would, if that were true, it would mean jam more rocks in, more resistance, and you'll get more current. Water will flow more quickly. When you say it in words, you say, "Oh, that can't be right," right? So you now know it had to be which one?
Inverse.
So yeah, it's an inverse relationship. So it's really 1 over R. And so that means when R increases, the current decreases. Does that make sense?
Yeah.
On the other hand, you don't have to increase the resistance. What if you take some rocks out of the hose? Then you're decreasing the resistance. What will happen to the current?
Increase.
It'll increase. It'll flow more easily, right?
Yeah.
Okay. So these three things now come together to create what's called Ohm's law. And now I'm ready to show you that. So I'm going to erase the board. Okay?
All right.
Okay, I'm going to erase this. This is called Ohm's law. So we're going to start with the voltage is proportional to current. Oops, I didn't mean to do that. We're going to start with current is proportional to voltage, and current is inversely proportional to resistance, because of the ideas we just had said, right? More voltage, more current, right?
Yeah.
Less voltage, less current. Then when you look at the second line here, inversely related, because more resistance makes less current, and less resistance makes more current, right?
Yeah.
So now we just combine these, and we create an equation. I equals, do you know what it will be?
I equals 1 over.
Where will V go in our equation, on the top or the bottom?
Top.
Top, yep. Where will R go?
At the bottom.
Bottom. That's it.
R.
Yep, that's an equation called Ohm's law.
Mm-hmm.
And it means that you can calculate how much current will flow in your wire as long as you know how much voltage there is and how much resistance there is.
Got it.
It's actually very, very similar to Newton's second law, acceleration equals F over m, which is really normally written F equals ma, right?
Yeah.
Same idea. I is the flow of current, how quickly it's moving. Acceleration is kind of like that. That's how quickly you speed up, right?
Mm-hmm.
Is voltage kind of like force? Is voltage a push? Yeah. Voltage is what pushes the electrons through, so it's like a force, right?
Yeah.
And then back to Newton's law, A equals F over m. Is m, known as the inertia of something, also a resistance to a change in motion? If you have a high mass, like a Mack truck, is that a lot of resistance to somebody getting you moving?
Yeah.
Yes. So see how that's in the denominator, and in Ohm's law, resistance is also in the denominator, you see?
Mm-hmm.
It's a very similar idea. And just like when I wrote A equals F over m, most people don't remember it that way, just remember F equals ma, right?
Mm-hmm.
Because you could cross multiply over here and get F times 1 is F and m times A is ma, right? We could do that for Ohm's law, and we would get V equals IR. If we put this over 1, V times 1 is V, I times R is IR. So this is the one that people often remember, V equals IR. It's Ohm's law. But it makes sense to teach you Ohm's law by saying V over R, because then I was able to talk about the proportions, that I and V are proportional and that I and R are inversely proportional, because those kinds of things make sense. See what I mean?
Yeah.
And so that's Ohm's law, V equals IR. And you can use it to either calculate voltage, if someone gives you the current, I, and gives you the IR. But you could use it to calculate current. Maybe they tell you V and R and say find the current. Or they tell you to calculate R, and they give you voltage and they give you current and say solve for the resistance. So let's now now we're finally ready to look at number 4. In fact, can you try 4? That's your next homework problem.
Yeah.
So note that when you see 120V, V stands for volts. And 4.6A, A stands for,
Amplitude.
good guess, but in electricity, A stands for amps.
Oh, yes. Oh.
Yep. So 120V means 120 volts, and 4.6A means 4.6 amps. V is voltage, and amps is current, right?
Yeah.
And so now you're using Ohm's law to do number 4, which is you can use V equals IR.
Okay.
Yep, that sounds about right. So when you solve, you use V equals IR, which is now known as Ohm's law. When you solve it for I, you get V divided by R, right? Divided by a resistance of 4, I'm sorry. Oh, my fault. Let me back up.
Yeah.
I made a
It's
mistake.
for R.
Yep, you got it. We're solving this for the resistance. So we get V divided by I. So our voltage was 120 volts divided by current of 4.6 amps.
Got it.
Yep. Oop, a second. Yep, I get 26 or so, 0.1. And now the unit symbol is like that. And that's called ohms.
Mm-hmm.
So that means you have 26 ohms of resistance inside of this toaster oven.
Okay.
If the toaster oven had twice as much resistance, what would happen to the current? If the toaster oven, let's just say your answer that you got, let's just say the answer that you got was the number 25 instead of 26.1. So let's say it's a
26.09.
Okay, yep.
You rounded up to 1.
Yeah, that's, yep. Yeah, it would be 0.09. But technically we have, I mean, it depends on if you're doing significant figures or not. But if you weren't significant figures, then there would only be two significant figures. So you'd actually only be able to, your answer would actually just be 26. But yeah, if you rounded to 1 decimal, it would be 26.1. If you round to 2 decimals, it would be 26.09. So the question is, let's just say your answer was 25 ohms. So that means this toaster has 25 ohms of resistance. And the current they gave us, there was 4.6 amps of current flowing when the toaster oven was on, and it was 120 volts, which you should know that all of our houses, everywhere in America, every building, any wall outlet is 120 volts.
Okay.
So that's why they didn't randomly choose 120 in this problem. It's because everything is 120 volts. And so the question is, if the resistance of our toaster oven wasn't 25 ohms, but it was 50 ohms, what would happen to the current?
The current would decrease.
Yes. So if we double the resistance from 25 to 50 ohms, what would the new current be in your toaster oven? Because originally it was 4.6 amps.
Yeah.
When it was 25 ohms of resistance. But if you now double the resistance up to 50 ohms, what would your new current be?
5.2.
Okay, so let me just come back to this idea here for you. That current is inversely proportional to resistance, right? So if we're doubling our resistance, R is going up by a factor of 2. What will the current do? Since I and R are inversely proportional.
Decrease by a factor.
Yeah, exactly. So what would the new current be? Not 4.6 amps. What would the new one be?
The new one would be 2.3.
Yeah, you got it. Good job. What if, on the other hand, we take our toaster oven and re-engineer it so that it's not 25 ohms, but it's now only 12.5 ohms? What would our new current be?
So it was 25 ohms?
Yeah, if it's not 25 ohms anymore, when it is 25 ohms, there's 4.6 amps. But now we're going to redesign our toaster oven so that it only has 12.5 ohms of resistance. What would our new current be in our toaster? So if we go from 25 ohms to 12.5 ohms, are we reducing the resistance or increasing the resistance?
Reducing.
By what factor?
Factor
2. And so since their current and resistance are inversely proportional, if we decrease the resistance by a factor of 2, the current will do what?
Increase.
Increase by a factor of 2, which would mean that our new current should be what number?
9.3.
Yeah, exactly. Yep. And does that make sense? Because it would have less resistance to the flow of electricity. If you decrease from 25 ohms to 12 ohms, that means there's less resistance. That means the current will flow more rapidly, and it will be not 4.6 amps, but 9.2 amps, much more current, specifically twice as much current. Does that make sense?
Yeah.
All right. So let's try your next one, which is number 6. I'm going to erase this board. So let me just give you a little information here. Remember before we said that current was defined as delta Q over delta T?
Yeah.
Well, if we cross multiply, we would get delta Q is equal to I times delta T, right? And so people use this idea to describe how much charge, delta Q is charge is on a battery. So if you look at number 6, they describe a 75 ampere hour battery. So ampere is just really short for amp. That's actually the guy's last name. It was named after him, and his last name was Ampere. And we normally just shorten that to amp. Okay? But you can go to stores and buy batteries. And you can go to places and buy batteries even for phones and stuff, right? And they'll tell you how much charge you would expect on that type of battery. And they vary. You can get some charging units that have a little bit of charge stored on them. So when you try to charge your when you try to charge your phone, since there's just a little bit of charge in the battery pack, it only charges like 25% of your phone, and then that's it. On the other hand, you can buy a charger for your phone that has a lot of current, a lot of charge stored on it, and when you charge your phone to it, it'll not only charge your entire phone one time, but 3 times, because there's lots of charge on that battery pack. Okay, and they define how much charge is on that battery in this term called ampere hour. And so notice amps is current. You see that? And an hour is time. You see that?
Yeah.
So what that means is if you have a 75 amp hour battery, it means it can deliver a current at 75 amps for 1 hour. And then it would be dead. On the other hand, because if we said that's a certain amount of charge, 75 amps flowing for 1 full hour would be a certain amount of charge that's come out of that battery. On the other hand, you can use the same battery to do 37.5 amps for 2 hours. Because what is 37.5 times 2?
37.5 times 2.
75, right?
Yeah.
What is 75 times 1?
75.
Still 75, right?
Yeah.
So the point is, if you got a certain amount of charge on your battery, just like imagine you have a giant container of water. You can either poke a tiny hole in the bottom of that container and it will flow out at a very low current, but it'll take a long time for it to empty, right? giant hole in it, and now you're going to have much more current flowing from that giant hole. Water will flow out of it much more rapidly, but it will take much less time for it to empty. Right?
Yeah.
So in either case, you're emptying this container of water, and you have the choice of whether you want to let it to empty at a very slow rate, like the tiny pinhole in the bottom, and therefore it will deliver a slow stream of water, but for a long, long time. Or you can decide to empty it at a very rapid rate, which is a very high current, but it will only maintain that high current for, I don't know, a minute or two, and the whole container is empty.
Right.
So the point is, when you're talking batteries, how long that battery lasts depends on how much current are you drawing from that battery. If you're drawing 75 amps from that battery for the 75 amp hour battery, then you'll only be able to the battery will only be able to maintain 75 amps for 1 hour, and then it'll be empty. On the other hand, you can draw only 37.5 amps for it from that battery, but now it can maintain that for 2 hours, and then it will be empty. You could also do whatever, if I divide that by 2 again, I'm going to write on the bottom right of the screen, I could do 17.5 amps from this battery for 4 hours. And when I multiply those together, what number do I get? 75. Do you see that idea?
Mm-hmm.
So we use this idea called amp hours to define how much total charge is on the battery. You get to decide how long you want that battery to last based on how much current are you drawing from the battery. If it's a very high current that you're drawing from the battery, it's going to deplete very quickly. On the other hand, if you're drawing current from the battery at a slow rate, low amps, it'll maintain that for many more hours and then die.
Mm-hmm.
Okay, and so, I mean, it's no different with your smartphone, right? If you have a smart brightness all the way up to high, is that depleting your battery in your phone at a rapid rate? If it's a fully bright screen?
Yeah.
Yeah, that means that you're taking it out at, let's say, 75 amps, and then, which is not true, of course, it's way less than that, but let's just illustrate the idea. You slide the brightness all the way to the right, that super bright screen, it's 75 amps, 1 hour later, your phone's dead. On the other hand, you can slide the brightness down to a relatively dim, and it will now be only 17.5 amps, but it will maintain that for 4 hours, and then your phone will be dead.
Mm-hmm.
So we use, again, amp hours to quantify how much charge is stored on a battery. And so with that being said, let's look at your next question, which is number 6, I think. Number 6. Remembering you can always use Q equals I times delta T. Are there a 75 amp hour car battery? Just remember, though, is hour the right unit for time?
1 second.
No, it has to be in seconds. It's a pain in the butt, but when they give you things with hours, you have to convert it to seconds. So what out of Q, I, and delta T, out of those 3 things, in number 6, which one are you being asked to solve for?
Moving self-test for coulombs.
So which one would that be, Q, I, or delta T?
Q.
Q, yep, exactly. That's the one you're solving for. What would we do about this I delta T? You might think, hey, I can just put in 75 in for I, because that's amps, and then I can put the number 1 in like that, and just call the right side of the equation 75 times 1, which is 75, and that's it. Q is 75, done. Well, is that right?
No.
No. What do you have? You have to convert it to seconds, correct. So that's the only step, really, for that one. And you already had that from before. I think it was 18,600 or something like that.
That was for 5 hours. For 1 hour, it would be,
Oh, yeah, you're right.
3,600.
Yes, good, yep. So where would you put that number, 3,600?
In for T.
Yep, exactly. So 75 amps would go in for I times 3600, and that would be in seconds.
That would be 70,000 coulombs.
Yep. So it would be 270,000 coulombs, although something doesn't seem right, but that's a lot of amps. Is that right? Yeah, that is right. Because can I point out that even if it was a 1 amp current, a 1 amp current is 1 coulomb per 1 second, right? So if you have just 1 amp, it's 1 amp for 1 second is a full coulomb of charge. And you're doing not 1 amp, you're doing 75 amps, and you're not doing it for 1 second, you're doing it for 3,600 seconds, right?
Yeah.
So it makes sense that our answer is huge, right?
Yeah.
Yeah. So that's that. That's what that is. Now, can I ask another critical thinking question?
Yeah.
So again, you have a 75 amp hour battery, the one we've just talked about. If you don't draw electricity from it at a rate of 75 amp hours, I'm sorry, at a rate of 75 amps, but instead pull 0.5 amps, how many hours would it go for before the battery was dead? If the current coming out is now not 75 amps, but 37.5 amps.
Then it would be you said 35.5.
Yeah, it happens to be that 37.5 is half of 75. So if you cut,
then it would be half.
yes, so you're cutting the current in half. What will happen to the time that it can operate for, this battery?
It would decrease.
We're pulling less current from it, so does that mean it'll give us that less current for less time, or that less current for more?
Less current for more time.
More time. So how many hours would it be? How many? It can do 75 amps for 1 hour. But if you say, I don't want 75 amps for 1 hour, I only want 37.5 amps, how many hours can it give you?
30 minutes.
So that would be less current would be more time, right? So it would be 2 hours. 2 hours, right? And let me point that out. Can you look at the white screen for one more second? If you put in the number 37.5 amps here, right? And we said, now we want to get 2 full hours. 2 full hours would be 7,200 seconds, right? It'll be twice as many seconds as you had before, right?
Yeah.
If you multiply 37.5 times 7,200, what number are you going to get? Do it on your calculator.
Yeah, I get the same answer.
Right. So what is that trying to tell you? It's trying to tell you that there's 270,000 coulombs on this battery. And it doesn't matter if you decide to draw electricity from it at 75 amps for a full hour, then you'll withdraw all 270,000 coulombs from the battery. Or, in my second line, or you can draw electricity from it at a rate of only 37.5 amps for 2 hours, which is 7,200 seconds. How much electricity will you charge, will you deplete from that battery? The same amount, 270,000. It would be like my container full of water. Let's say it was 10 gallons of water in my container. You poke a tiny hole in it, and it delivers a little current for many, many hours. And we say, how much current, how much water did it drain from this container? 10 gallons. Then you fill it back. It delivers a huge amount of current for only a couple minutes, and then it's empty. And we say, how much water did it drain from the container? 10 gallons, right?
Yeah.
Does that make sense? That the total amount of water inside the container is always the same. Just like your answers there were both 270,000 coulombs. That's the total amount of charge on the battery, which is similar to how much water is in your container.
Right.
And how rapidly you deplete it depends on how quickly it's coming out. So that's that one. Let's see, might be able to fit in one more. We got 5 more minutes. The next one is 8. So why don't you try number 8? It'll be the last one we do.
All right.
I'll give you just a little hint that you get to use Ohm's law for this one, number 8. V equals IR. And you should know that when you're dealing with resistance, if this was, let's say, 1 meter of wire, let's say 1 meter of cable and I'm just making this up, has 5 ohms of resistance.
Yeah.
That means if you decide to take 2 meters of that cable, that means this 1 meter has 5 ohms, and this next meter also has 5 ohms, and another full meter also has 5 ohms. So if you had 2 meters of this wire I'm drawing on the board here, 2 meters would be 10 ohms. 3 meters of the wire would be 15 ohms. 4 meters of the wire would be 20 ohms. So longer cables have more resistance.
Yeah.
So that idea and Ohm's law is really what you're using to try to solve number 8. And the word potential difference, there's a word in your problem that says potential difference.
Yeah.
Potential difference is, and since we're running out of time, I can't go into too much detail about that, but I can tell you that's what you can think of as volts.
Right.
It's a fancy word for voltage, or really the difference in voltage between 2 points. But since we're only got 3 or 4 minutes left, just know that you can still do this problem by, when you read what are they asking me to solve for, what is the potential difference? Really, that is, what is the voltage for the bird's feet, on the bird's feet?
Well, V equals IR.
So you're really solving for V. And then do they give you current?
Yeah.
Yeah, 4,100 amps. That's a lot, but it's a transmission line, like shown in the picture there. And then they're saying the line itself has 2.5 times 10 to the minus 5 ohms of resistance per 1 meter. Remember the picture I showed you about the meters?
Yeah, in this 4 centimeters.
In this case, there's only 4 centimeters of that wire. So how would you figure out the resistance of 4 centimeters of length? So you're really imagining going over to that transmission line and cutting off a 4 centimeter segment and wondering, I wonder how much resistance that has. Based on the fact that they tell you, if it were 1 full meter of wire, it would have 2.5 times 10 to the minus 5 ohms. So I'm going to add one more note for you. This idea that longer cables have more resistance means that resistance is proportional to length.
Okay.
So that means if the cable's 2 times longer, it has twice as much resistance. If the cable's 20 times shorter, then it has 20 times less resistance.
Got it.
So how are you working out the resistance of that 4 centimeters?
Well, I converted the 4 centimeters to meters.
Perfect.
And then I multiplied that by the 2.5 times 10 to the negative 5.
Excellent.
Then I got 1 times 10 to the negative 6.
Excellent.
Now I'm plugging that into the equation. So I have 41 times 10 raised to the negative 6.
Yep. That's correct. So 1 times 10 to the minus 6 ohms is the actual resistance of the 4 centimeters, right?
I got 0.
0 for what?
For voltage.
So now, wait, let's just back up one. The resistance of that 4 centimeter wire, you got 1 times 10 to the minus 6, is that right?
Yeah.
Okay, so now you're one step away from solving. Maybe there's a setting on your calculator that's just rounding that off as 0. Where that setting is in a minute. But to solve the problem, you would now do the voltage is the current, which was 4,100 amps, multiplied by the resistance, which we found, which we found to be 1 times 10 to the minus 6. So it turns out when you take 4,100, because 1 times 10 to the minus 6 is really 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So that's the number right there. 1 times 10 to the minus 6 is really 0.000006. When you multiply that by 4,100, I'm getting 0.0041.
Yeah, mine's just rounding off this.
Yep. So I can show you where that is. If you go, let me see, mode. So go to, you know where the mode, do you have a graphing calculator?
Yeah.
Okay, press mode next to the second button on the top left.
Got it.
And then 2 rows down, it'll say float, and then it will say 0, 1, 2, 3. What is your black box on?
2.
That's why. You want to put that on float.
Oh, what's mine?
Yep. And then retry it. You should get 0.0041.
Yeah, I got 0.041.
All right, yeah. So just to give you a sense of what that's trying to tell you, that's a small amount of voltage, right? 0.0041. Just a AA battery, one single AA battery has 1.5 volts, right? So if you could connect that bird to a 1 AA battery, do you think you would electrocute the bird and kill it? Do you think 1 AA battery could kill a bird?
No.
No, the answer is no, it can't. And that AA battery has 1.5 volts. On that line that he's sitting on, how much voltage is being applied to him? 0.0041 volts. Is that going to kill him?
No.
No, it's not nearly enough voltage. It's not because the voltage of the line is low, hundreds of thousands of volts. The voltage that's actually being applied to the bird depends on the distance between his 2 feet. And since he's only 4 centimeters apart on his 2 feet, a very small fraction of the total voltage on the line is actually applied to him, and that's why he's safe. If his feet were a mile apart, he would get fried. But and that's actually a complex idea that I'm trying to say very quickly, but we're out of time, unfortunately. All right, Jeremy, I hope that was helpful for you. And let's see, what did you have? You still had a lot left, I guess, but give it your best. You have 8, 30, 32, 34, and 36. Actually, before I go, just 1 second. 30, what do we say? 30, 30. Wait, what number was that? 6 or 8? That was number 8. 30, 32, 30. Let me tell you one thing.
Okay.
That you'll probably need to read in your book about what's called power, electrical power.
Yeah.
So I'm just going to very quickly tell you, power is measured in watts, like the wattage, and power is voltage multiplied by current.
Okay.
So V times I is power. So that would be in your book, and you'll need to utilize that for number 30.
Got it.
And then 30. Oh, then wait, what happened? Oh, I only got through. What happened to 32, 34, and 36? Oh, I guess I only got through 30. I thought I saw the other ones before. You only sent me through 30, but give me 1 second. I thought I saw them all before. One moment. No, I guess not. You only sent me through. Oh no, there they are. 32. Number 32 uses the same equation: power equals voltage times current.
Okay, gotcha.
So really, just that when I've given you now power equals voltage times current, and I would recommend still reading in your book so you better understand it. But once you're equipped with Ohm's law, V equals IR, as well as power equals voltage times current, you can solve most problems.
Okay.
And I guess one last thing to tell you, and then I'll end it. If an electrical appliance is a 5-watt appliance, it means that it's drawing 5 joules of electrical energy for every 1 second that it's on. If it's a 100-watt appliance, that means it's drawing 100 joules of electrical energy for every 1 second that it's on. So that's what watts means, which is related to power. Power is watts. All right?
Yeah.
All right. Good luck, Jeremiah, and I'll plan to see you next week. Have a good weekend.
You too.
Bye-bye.
Bye-bye.
That concludes today's visit with Jeremiah.